Hello and welcome to our students. Today's lectures we have going to discuss the new topic chemical thermodynamics. Chemical thermodynamics are studied in at FYBSc level. For these chapters we have see the various laws of chemical thermodynamics. So chemical thermodynamics deals with various applications of the laws of in chemical system. The concept of free energy, which is important, can be used to predict the spontaneous nature of chemical processes. The change of free energy can be used in the study of equilibria, physical as well as chemical properties. The concept of chemical potential as a particular case of class of properties called as partial molar quantities. Its variation with temperature, pressure, and its application, they will be discussed in these chapters. So firstly, we have see the free energies. So two types of free energies functions we have see like a Helmholtz free energy and Gibbs free energy. Firstly, we'll learn the Helmholtz free energy. Helmholtz free energy or this work function capital A is can be defined capital A is equal to U minus Ts as equation 1 and gives free energy can be defined capital G is equal to H minus Ts. For the small change of this equation 1 we get for small change then this equation first becomes delta A is equal to delta U plus T delta S equation 3. But you know that the change of entropy like delta S is equal to Q reverse upon T. So this equation third becomes therefore delta A is equal to delta U minus T delta S minus Q reverse. So how will you this simplify equation or rearrange this equation? T delta S is equal to Q reverse. So delta A is equal to delta U minus Q reverse. So the change of entropy delta S is equal to Q reverse upon T. Then this equation third becomes delta A is equal to delta U minus Q reverse. From the first law of thermodynamics, delta U is equal to Q reverse minus W max or minus W max is equal to the delta U minus Q reverse, and therefore this equation can be becomes like the delta A is equal to W max or minus delta A is equal to W max or minus W max is equal to delta A. And therefore change in the Helmholtz free energy is equal to maximum work functions, which is known as the Helmholtz free energy for the maximum work functions. Next, Gibbs free energy. Gibbs free energy capital G is equal to H minus Ts. For small change, then the equation 1 becomes delta G is equal to delta H minus T delta S. But delta H is equal to delta U plus P delta V. put this value in above equation, we get delta A is equal to the delta U minus the T delta S. So this delta H is equal to delta U plus P delta V, and delta A is equal to delta U minus T delta S. By comparing these two equations, we get then delta G is equal to delta A plus P delta V, equation 3. But we know that the Helmholtz free energy delta A is equal to minus W max. Therefore, this equation becomes delta G is equal to minus W max plus P delta V, equation 4. But you know that the P delta V as the work of expansion, and therefore this equation becomes like delta G is equal to minus W max plus W of expansion. W expansion means work of expansion, and therefore minus W max is minus W expansion, and therefore the delta A, like a Helmholtz change of Helmholtz free energy, is equal to minus W n e the net work of work function, net work functions. Therefore, delta A is equal to the net of this work done, that is the decrease in Gibbs free energy of a process at a constant temperature and pressure is equal to the net work which can be obtained from the system. It is therefore known as the net work function. The next points we have see the variation of Gibbs free energy with temperature and pressure. This, firstly, you know that the change of free energy capital G is equal to H minus Ts, as this equation 1. For infinitesimal change for this equation, we get dg is equal to dh minus tds minus sdt, equation 2nd. But you know that according to the first law of thermodynamics, the H is equal to E plus PV, and therefore dH is equal to du plus pdv plus vdp for infinitesimal change for this equation. So this new equation we get like dH is equal to du plus pdv plus vdp, equation 4. From the first law of thermodynamics, are know that du is equal to dq plus dw. For reversible change, dw reverse is equal to minus pdv and dq reverse is equal to tds. Repeat again. For reversible change of the reactions or for reversible process, dw reverse is equal to minus pdv and dq reverse is equal to tds. Then dq reverse is equal to tds. From these two equations we can compare and to get dq reverse is equal to tds. So substituting this equation in 5, we get then du is equal to TdS minus PdV. Equation 5 are like du is equal to dq plus dw. Then dq reverse is equal to what is TdS and dw is equal to minus PdV. For this equation 5, then we get dq reverse is equal to TdS. So du is equal to TdS minus PdV. Then substitute the equation this in equation 4 and then equation 2 we get. Firstly, these 6 equation we put equation 4 we get. See here equation 4th dH is equal to du plus PdV plus PdV. So we are C is here. This du is equal to TdS minus PdV. Put this value in this equation 4th. du is equal to TdS minus PdV. So this equation for dH is equal to du is equal to what is TdS minus PdV plus PdV plus PdV. And then this value of dH, put this equation 2 are here and therefore dg is equal to here dg is equal to TdS minus PdV plus PdV plus PdV minus TdS minus SDT. So solve this bracket, then we get TdS minus PdV plus PdV plus PdV minus TdS minus SDT, equation 8. And therefore this plus TdS and then minus TdS will get cancelled. Minus PdV plus PdV they will be cancelled, and therefore dg is equal to what is the remaining PdP minus SDT, then equation 9.